the small measurement error that changed the cosmos. At first, it looked like nothing more than a nuisance, a tiny discrepancy buried deep inside tables of numbers that almost no one outside a narrow field would ever notice. A fraction of a percent, a mismatch so small it felt embarrassing to mention. And yet that small error refused to disappear, no matter how carefully the universe was measured. To understand why this error mattered so profoundly, we have to return to a moment when cosmology believed it was close to completion. The universe was expanding. That much was clear. Galaxies were rushing away from one another, and space itself was stretching. The only remaining question seemed simple. How fast was this expansion happening? Exactly. This number mattered more than it appeared. It determined the age of the universe, its size, its fate. A faster expansion meant a younger cosmos. A slower one meant an older, more settled universe. Everything depended on measuring this single value correctly. Astronomers built entire careers around refining it. Better telescopes, better calibration, more distant galaxies. Every improvement was meant to shrink uncertainty and reveal the true rate once and for all. Confidence grew with every decimal place added. But as measurements improved, something unsettling happened. Different methods produced different answers. Not wildly different, not obviously wrong, just incompatible enough to cause discomfort. Two values emerged, both precise, both carefully measured, both impossible to reconcile. At first, this was treated as technical friction. One method must be flawed. One dataset must hide bias. Systematic errors were suspected everywhere. Calibration was questioned. Distances were rechecked. Assumptions were audited line by line. Yet the disagreement remained. In fact, it sharpened. As instruments grew more precise, the gap widened. The universe was not converging toward a single answer. It was insisting on two. This was deeply troubling. Physics thrives on consistency. When independent methods agree, confidence follows. When they do not, something fundamental is being missed. And here, the disagreement was not noise. It was persistent, structured, defiant. One measurement looked at the nearby universe. It tracked stars, galaxies, and cosmic candles. The other looked deep into the past. It examined the ancient radiation left behind by the early universe itself. Both were measuring the same thing, and yet they disagreed. This tiny measurement error was no longer small. It threatened the foundations of cosmology. If both measurements were correct, then the universe was hiding something new, something unaccounted for, something that had quietly shaped expansion from the beginning. What seemed like a technical annoyance had become a crack in the cosmic story. And through that crack, physics began to glimpse the possibility that the universe was not behaving the way its equations demanded. As this discrepancy refused to fade, cosmologists were forced into an uncomfortable position because the disagreement was no longer between rough estimates, but between some of the most precise measurements ever made. Each method was internally consistent. Each had been tested, corrected, and refined repeatedly, and yet the numbers would not meet. The universe was delivering two answers to the same question. One value came from the early universe. It relied on the cosmic microwave background, the faint afterglow left behind shortly after the Big Bang. By studying tiny temperature variations in that ancient light, physicists could reconstruct the universe's initial conditions with extraordinary precision. From those conditions, the expansion rate could be inferred. The math was clean. The model was elegant. The uncertainty was small. The other value came from a nearby universe. It was measured directly, using stars that pulsed, exploded, and shone with predictable brightness. By comparing how bright they appeared to how bright they truly were, astronomers calculated distances. By combining those distances with observed motion, they measured expansion directly. This method did not rely on early universe assumptions. It measured what was happening now. For years, scientists assumed one side would eventually give way. Perhaps the early universe model was missing a detail. Perhaps local measurements hid subtle bias. But the more carefully each side was examined, the stronger each result became. Error bars shrank. Confidence rose. Agreement did not follow. This turned a measurement problem into a theoretical crisis. If both methods were correct, then the universe had evolved differently than expected. Something must have changed expansion after the early universe. Something invisible, something unaccounted for by existing models. The equations of cosmology were suddenly under suspicion. They assumed certain components: known matter, dark energy, radiation, gravity behaving predictably. But the numbers suggested an extra ingredient, a missing influence shaping cosmic history. This possibility was both thrilling and dangerous. Adding new physics could resolve the tension, but it would also mean rewriting a model that had worked remarkably well. The standard picture of the universe was not failing loudly. It was failing quietly, by a few percent, by just enough to matter. Cosmologists gave the problem a careful name. Not an error, not a mistake. A tension, the Hubble tension, a polite word for a deep fracture. As the tension persisted, its implications grew heavier. If the universe's expansion rate truly differed between past and present, then cosmic history was incomplete. Something happened between then and now, something subtle, something powerful, and physics had not noticed it yet. This small measurement disagreement was no longer about numbers. It was about whether the universe had been fully understood at all. And the longer the disagreement survived, the clearer it became that the cosmos was guarding a secret, one hidden not in dramatic explosions, but in the quiet refusal of two precise answers to agree. This is where the tension transformed from an academic debate into a profound existential challenge for cosmology, because the universe was no longer disagreeing casually. It was disagreeing stubbornly, consistently, and with a confidence that suggested intention rather than error. Every attempt to smooth the discrepancy failed. Every refinement sharpened it. The more carefully reality was measured, the more loudly it insisted on contradiction. Physicists began exploring every possible explanation, starting with the most conservative ones. Perhaps measurements of stellar distances were subtly biased. Perhaps cosmic dust interfered with brightness. Perhaps calibration errors compounded quietly. Teams reanalyzed data independently, cross-checking assumptions line by line. Nothing collapsed. The numbers held firm. Attention then shifted to the early universe. Maybe the cosmic microwave background was being misinterpreted. Maybe tiny assumptions about primordial matter were wrong. Maybe neutrinos behaved differently. Maybe unknown particles influenced expansion early on. But every modification that fixed one side broke another. The model resisted change like a lock system. This resistance was deeply unsettling because the standard cosmological model had been astonishingly successful. It explained large-scale structure. It predicted background radiation. It matched galaxy distributions. It worked almost everywhere. And yet here, in one crucial place, it failed just enough to matter. The universe seemed to be hinting at something subtle rather than dramatic, not a violent new force, not an obvious breakdown, but a gentle deviation woven into cosmic history, something that altered expansion quietly, something that left fingerprints only in precision. Speculation grew bolder. Maybe dark energy was not constant. Maybe it evolved over time. Maybe gravity behaved differently at large scales. Maybe additional dimensions leaked influence. Each idea carried enormous consequences, each risk destabilizing physics as it was known. What made this conflict so difficult was its restraint. The universe was not screaming. It was whispering. The discrepancy was small but persistent, large enough to be real, small enough to evade obvious explanation. It sat precisely in a range where discovery hides. This placed cosmology in a dangerous position. Ignore the tension and risk missing new physics. Chase it recklessly and risk inventing ghosts. The line between insight and overinterpretation grew thin. Caution and curiosity pulled in opposite directions. The measurement error was no longer about technique. It was about trust. Could physics trust its most successful model, or was success blinding it to a deeper truth? The universe was challenging confidence without overthrowing it. At this stage, the cosmos felt almost adversarial, as if it were daring humanity to look closer, not through bigger telescopes, but through deeper understanding. The answers were not hidden in noise. They were hidden in precision, and that made the situation even more unsettling. Because if the universe was truly expanding differently than expected, then something fundamental had changed since the beginning of time. And whatever that change was, it had shaped everything that followed without announcing itself. The climax of the story is not a dramatic revelation, but a quiet confrontation with uncertainty so precise that it cannot be dismissed, because the universe has revealed a disagreement that refuses to be explained away, a difference measured carefully, repeatedly, and independently, a difference small enough to hide from casual attention, yet large enough to threaten the foundations of cosmic understanding. The cosmos did not break loudly. It drifted subtly off script. What makes this moment extraordinary is not the size of the error, but its persistence. Physics expects noise to fade with better data. Mistakes shrink under scrutiny. But this discrepancy did the opposite. It hardened. It survived better instruments, larger surveys, and stricter analysis. Reality did not converge. It diverged. This forces an uncomfortable realization. The equations describing the universe may be incomplete, not wrong. Incomplete. They describe most reality beautifully, yet miss something delicate that only precision can reveal. A hidden ingredient, a gentle influence, a modification so restrained that it escaped notice for decades. If this tension points to new physics, it will not arrive as a revolution. It will arrive as correction, a refinement, a small addition that changes everything quietly. The universe may be more complex than the story told so far, not by breaking rules, but by adding one more. This moment reshapes how discovery happens. Progress no longer comes from bigger explosions or stranger particles. It comes from disagreement at the 5th decimal place, from numbers that refuse to align, from precision so sharp it cuts through confidence. The cosmos is not hostile. It is patient. It allows misunderstanding to persist until measurement becomes unavoidable. Then it reveals a flaw so small it can be ignored, until ignoring it becomes impossible. This is how physics moves forward now, not by overturning reality, but by listening closely when it whispers. The universe is not shouting new laws. It is hinting at them. Whether this tension leads to new forces, evolving energy, or deeper geometry remains unknown. But one thing is clear. The universe is not finished being understood, and it is not obligated to agree with our expectations. So, what do you think? Are we witnessing the first crack in a complete cosmic story, or just the beginning of a much deeper one?